Hello everyone, my name is Andrei Tankich. I'm a master's student at the HAC University. Today I will present a paper called Revisiting Optimal Resilience of Fast Byzantine Consensus. This is joint work with Petr Kuznetsov from Telecom Paris and Yan Zhang from the San Jose State University. In this paper, we establish optimal resilience for fast Byzantine consensus. An N-process protocol can tolerate F failures if and only if N is at least 5F-1. This improves the famous FaB Paxos protocol. We consider a classic model with a fully connected partially synchronous network of processes, which communicate by sending messages. Some processes may be Byzantine faulty, which means that they are controlled by a malicious adversary and can deviate from the protocol arbitrarily. Consensus is inherently slow in the worst case. Even if the network is synchronous from the beginning, it requires at least F+1 communication delays. Hence, most practical algorithms optimize for the so-called common case, when all processes agree on the same correct leader and the network is synchronous from the beginning of the execution. For example, the common case latency of Paxos is just 2 message delays. However, if we want to tolerate Byzantine faults, the latency becomes higher. In particular, the most famous protocol, PBFT, requires 3 message delays even in the common case. To close this latency gap between the crash fault-tolerant and Byzantine fault-tolerant algorithms, Jean-Philippe Martin and Lorenzo Alvisi proposed FaB Paxos, a Byzantine fault-tolerant partially synchronous consensus protocol that terminates in just 2 message delays. However, FaB Paxos has significantly worse resilience. To tolerate F failures, it needs 5F+1 processes. Although in their original paper Martin and Alvisi claim that 5F+1 is the optimal number of processes, we show that it is not true and present a protocol that requires 5F-1 processes. In particular, when F is equal to 1, our protocol needs just 4 processes, which is optimal for partially synchronous Byzantine consensus, even if we don't require fast termination. Since the time of Paxos and view stamped replication, many partially synchronous consensus protocols have similar structure. They can be split into 3 parts. First, the view synchronization protocol allows all processes to agree on the same view number. The view number is then mapped to a leader process. Then the main protocol allows the elected leader to propose a value and drive the protocol to completion. Finally, if the leader fails to do so and a new leader is elected, view change protocol allows the new leader to select a safe value. Since the view synchronization protocol can be reused across different consensus algorithms, we just assume that it exists and focus on the main protocol and the view change protocol. First, let us look at simple crash fault-tolerant solution for the consensus problem. Here, the main protocol consists of 2 simple phases, propose and confirm. When a process receives n-f confirmations, it decides the value. In the view change, all processes vote by sending the last proposed message that they have received to the new leader. The leader then simply chooses the value with the highest view number. The correctness of this protocol relies on the fact that only one value can be proposed in a given view. Let us now build a simple Byzantine fault-tolerant consensus protocol. We will do so simply by enforcing the correct behavior and emulating the crash fault-tolerant solution. The protocol on this slide can be considered as a simplification of the famous PBFT protocol. First, in order to enforce the choice of a safe value during the view change, the processes will sign their votes with digital signatures, and the leader will follow the votes when it proposes a value. Also, in order to prevent the leader from proposing 2 or more different values in the same view, we will require the leader to collect signatures from a supermajority quorum before proposing a value. This technique is known as consistent broadcast. This simple protocol solves Byzantine consensus provided just 3 F+1 processes. However, its latency in the common case is twice as large as the latency of the crash fault-tolerant solution that we had before. But let us try to remove this additional round trip and simply allow a Byzantine leader to equivocate. maybe we'll still be able to somehow recover a safe value when a correct leader is elected. We must pay special attention to the case when a Byzantine leader proposes multiple values in the same view. We call this behavior equivocation. If one of the values is decided by a correct process, in order to maintain safety, all future leaders must choose this value in the view change. But how does the new leader determine which value to choose? Note that it cannot simply choose the value with the highest view number, as we did before, because there may be multiple such values if the leader of the corresponding view has equivocated. A simple approach would be to select the majority vote, but as demonstrated on the slide, with 3f+1 processes, this may lead to a wrong value being chosen. In 2006, Martin and Elvisi proposed a protocol called FaB Paxos that solves the problem of equivocation by increasing the number of processes. They show that with 5f+1 processes, the right value will always be in the majority. Their protocol relies on a simple quorum intersection rule. If the total number of processes is 5f+1, then any two quorums of n-f processes always intersect in at least 2f+1 correct processes. Hence, if some value is decided and then a view change is performed, at least 2f+1 of the votes will be for the decided value, and at most 2f votes for any other value. But let us try to reduce the number of processes. We will keep the main protocol the same. The leader simply proposes a value deduced from the votes. If in the view change we don't see two different values with the same view number, then we can just select the value with the highest view number, as in the original Byzantine fault-tolerant algorithms. But what do we do if there are multiple such values? Let us take a closer look at this case. Suppose that some process, while being a leader, issues a proposed messages with two different values, and one of these values ends up being decided by a correct process. If in the view change we try to select the value by simple majority, we may end up selecting a wrong value, which in the end will lead to a safety violation. However, we can observe that in this case, the new leader can deduce that the process that proposed two different values is Byzantine. Indeed, a correct process will never propose two different values in the same view. The new leader will be able to prove the fact of equivocation to other processes by showing two conflicting cryptographically signed signatures. Hence, among the remaining processes, there are at most f-1 Byzantine. The new leader can ignore the vote by one Byzantine process and wait for one more vote from a correct process. This will allow the new leader to make the right choice using the majority rule and propose a safe value. This slide illustrates the quorum intersection rule that our protocol relies on in case of equivocation. The main difference with the intersection rule used in FaB Paxos is the fact that now we know that at most f-1 Byzantine processes belong to the intersection of the two quorums. Here is the scheme of the solution. The main protocol remains the same as it has always been, and the view change protocol is adaptive. If it doesn't detect an equivocation, it uses the highest view number rule. Otherwise, it ignores the vote from the exposed Byzantine process and uses the majority rule among the other votes. However, there is one final caveat. If we implement the protocol as was described up until now, the sizes of the messages that are sent over the network will grow without a bound in executions with long periods of asynchrony. This happens because each vote contains a certificate, which is a set of votes from earlier views. Each of those votes, in turn, contains a set of votes from even earlier views, and so on. To overcome this issue, we can just add an extra round trip to the view change. It effectively compresses the certificate to just a linear number of signatures, or a single signature if we use threshold cryptography. Note that it does not affect the common case latency, as the view change protocol is not on the critical path. Finally, let us discuss the proof of optimality of the resilience of the proposed protocol. We didn't want to limit our discussion to leader-based protocols or protocols of some special structure. Hence, we defined a fast Byzantine consensus protocol in a very abstract way. Nevertheless, we showed that every such protocol must have what we call an influential process. Intuitively, an influential process is a process that can swing the decision in one way or another in some executions of the protocol. More precisely, there must exist two executions, where process P is the only process that has different inputs. The network in both executions is synchronous from the beginning, and all correct processes decide after two message delays. The Byzantine processes in these executions honestly follow the protocol during the first round, but become silent afterwards. Most importantly, the values decided by correct processes in these executions are different. Here is an illustration of two such executions. Row 1 is a P1 faulty two-step execution with consensus value x. This means that all processes, including the Byzantine ones, are active during the first round of the protocol, but the group of processes denoted as P1 are Byzantine and become silent in the second round. Everyone except the processes in P1 decide value x after the second round of message exchanges, which is represented by the green ticks. Similarly, row 5 is a P5 faulty two-step execution with consensus value y. The messages exchanged in the first round are identical in the two executions, except for the messages sent by the influential process P. Hence, we can say that the consensus value is determined exclusively by the messages sent by process P and the network scattering. We use this notion of an influential process to prove the lower bound by contradiction. We split all processes into 6 groups. The first group is just the influential process P. Groups P1 and P5 contain F processes each. Groups P2, P3, and P4 contain F-1 processes each. The total number of processes is 5F-2 because we want to prove that there is no fast Byzantine consensus algorithms that can operate on 5F-2 processes. We construct a chain of executions where the first and the last executions in the chain, row 1 and row 5, are the executions from the definition of an influential process. Moreover, each pair of the adjacent executions in this chain is indistinguishable for some correct processes. Hence, all these executions must have the same consensus value. However, by construction, executions row 1 and row 5 have different consensus values, and this is a contradiction. Here is the illustration of execution row 2. It is similar to row 1, but the influential process P is Byzantine and it equivocates. For the group of processes P1, it sends the same messages as in execution row 5, which is represented by the red arrow on the slide. For every other group of correct processes, P3, P4, and P5, it sends messages which are consistent with execution row 1, which is represented by the green arrows. Additionally, the processes in group P2 are Byzantine and they cooperate with process P. For the processes in group P3, they pretend that they have received the same message as in execution row 1. This is represented by the green arrow from P2 to P3 in the second round. For all other processes, they act in the same way as in execution row 5, which is represented by red arrows to all other groups. Finally, we delay messages from group P1 to group P3 so that they arrive already after the end of the second round. Hence, as can be seen on the slide, the set of messages received by group P3 is identical in executions row 2 and row 1, which means that these two executions are indistinguishable for this process, and they must decide the same value x after the second round. Similarly, we can construct execution row 5 in such a way that processes in P3 will decide value y. Again, the process P is Byzantine and Equivocates, but this time group P4 cooperates with process P and sends different messages in the second round. And messages from group P5 to P3 are delayed so that they arrive after the second round. Let us now compare executions row 2 and row 4 side by side. In these two executions, the correct processes in group P3 decide different values. For all other correct processes, the Byzantine group P2 in execution row 2 acts in the same way as in execution row 4. They send red messages. Symmetrically, the Byzantine group P4 in execution row 4 acts in the same way as in execution row 2. They send green messages which are consistent with execution row 1. Hence, the two executions are indistinguishable for all correct processes except the processes in group P3 as long as they don't receive any messages from P3. To show that the correct processes must eventually decide some value despite not receiving messages from P3, we construct the fifth execution, called row 3. In this execution, the influential process P sends red messages to groups P1 and P2 and green messages to groups P4 and P5. The processes in P3 are Byzantine and stop sending any messages starting from the second round. Since any consensus protocol must provide liveness despite any F processes being Byzantine, all correct processes must decide some value at some point. If in execution row 2 and row 4 we delay all messages from group P3 at least until this point in time, then this execution will be indistinguishable from both row 2 and row 4 for all correct processes except those in P3. Hence, any decision in this execution will lead to a contradiction. On this slide, the results are summarized. As can be seen in the table, with respect to the common case latency and resilience, the proposed protocol is strictly better than FaB Paxos. Moreover, when we need to tolerate just one failure, it is also strictly better than PBFT, as it provides better latency with the same number of processes. We also showed that the resilience of our protocol is optimal for a partially synchronous Byzantine consensus protocol with optimal common case latency. With this, I would like to thank you for watching the full video and invite you to read the paper in the proceedings.